Welcome to our session on band structure theory. So today we are going to look in more detail about how we can compute band structures in tie-bonding models in particular, and how we can use symmetries in the Hamiltonian to actually compute the spectra of Hamiltonians that have an infinite number of sites. This is something that we already did partially in the previous session, and we are going to build on top of some of the tricks that we developed back then. So just as a reminder, let us look at the one-dimensional tie-bonding model. So this is just a simple model where we have a chain of sites and there's a finite hop in between them, so that we write the Hamiltonian as C dagger I, Ci plus 1 plus the Hermitian conjugate. This Hamiltonian has a symmetry, which is translational symmetry. In practice, this means is that you can replace all the creation and annihilation operators in site n by site n plus 1, and your Hamiltonian remains invariant. If you think about this transformation in a matrix form, what this actually means is that the matrix form of the Hamiltonian commutes with the matrix representation of the translational symmetry operator. From linear algebra, we know that if two operators commute, there's an eigenbasis that it's common for both operators. And this is the eigenbasis that we want to use in this type of Hamiltonian. And in particular, for the translational symmetry operator, we know that the eigenstates of the translational symmetry have to pick a phase every time that we apply translational symmetry. This comes from the fact that since translational symmetry, and in particular, and in general symmetries, are unitary operators, their eigenvalues have to be complex numbers in the unit circle. This phase that states gain when the symmetry operator is applied is what we call the block phase of the wave function, which is the symmetry eigenvalue. And the block phase goes in the interval 0 and 2 pi, and this is what it's going to be related with the quasi-momentum in an electronic structure. Okay, great. So today, what we are going to essentially focus on is in demonstrating that if you have a Hamiltonian that has translational symmetry, and that it has an infinite number of sites, you can actually transform this Hamiltonian for an infinite system onto a set of Hamiltonians for finite systems. This is a continuous set of Hamiltonians that it's labeled by a parameter that it's the quasi-momentum or the symmetry eigenvalue. And these different Hamiltonians that are labeled by this parameter are what we call the block Hamiltonian. So they are Hamiltonians that depend on a parameter that it's the quasi-momentum. And every time that we see bands for a material or electronic structures for any quasi-particles, we are effectively talking about the eigenvalues of this Hamiltonian that depends on k as a function of k, as a function of the quasi-momentum or the symmetry eigenvalue. So today we are essentially going to use this trick for several different models and see what are the properties that we can learn of a material in this way. Okay, so in practice, we are going to look a little bit more in detail on how we can compute bands in the simplest case where we have just one orbital per unit cell. So the system is essentially a system that has translational symmetry with a single orbital. Then we will move on to consider multi-orbital systems, meaning that we have several orbitals per unit cell and this unit cell is replicated in real space. Then we will look at how we can use this idea that work in one dimension for higher dimensional systems. We will study different properties that we can extract from this eigenvalue dispersion that are in particular the effective mass, the density of states, and some others. And at the end, we are going to briefly discuss how we can compute, let's say, how these properties that we can compute theoretically can actually be measured in experiment using angle resolved photoemission spectroscopy. Okay, great. So maybe one of the most important ideas for today is that when we talk about band structures or electronic structures, we not only refer to electrons, but we can also refer to many other different quasi-particles. We can also have them for phonons, for magnons, and even for more exotic quasi-particles. Even though band structures are essentially tricks that we can use to solve single particle Hamiltonians, there are already a lot of extremely interesting physics happening in them. There's a lot of really exotic phenomena that we can understand just at the single particle level from studying electronic structures and band structures. And some of these examples are, for example, the emergence of direct fermions in materials. So the emergence of fermions that have a zero effective mass. We can also use band structure theory just to understand different types of topological matter, including, let's say, pile semimetals that are, let's say, generalizations of Dirac fermions to higher dimensions, and of course to understand topological insulators, in particular quantum spin Hall insulators, Chern insulators, crystalline topological phases, topological superconductors, and so forth. And this is something that we will use many, many times in the next few sessions. So all the mathematical tricks that we will develop for electrons, they can be systematically used for many other quasi-particles. Okay, so something that is also very interesting to note is that electronic structure and band structure theory is not only relevant for materials where we actually have electrons and orbitals, but it is also very relevant for artificial platforms where we can create quantum excitations subject to a certain periodicity, subject to a certain potential. And this applies, for example, to cold atom systems where we can actually create some effective lattices optically, and we can emulate different types of electronic dispersions in these artificial systems. And this applies also to many other platforms where we can emulate different types of electronic structures. So from now on, let us just focus on materials, but keeping in mind that these ideas can apply to, let's say, many different situations. So we are going to look at a system that is periodic in space and that it's made of atoms. So we have, for example, atom number 1 and atom number 2, and there are different localized orbitals in each one of these sides of the lattice. So even though we are going to focus on electrons, let me reemphasize again that we can actually use the very same tricks for any local quantum excitation that we may have in a material. So you can think that a local quantum excitation can be an electron, but it can also be a magnetic fluctuation such as magnon. It can be also a fluctuation of the location of the atom in real space, such as a phonon, or it can be a much more complex fluctuation like a Bogoliubov quasi-particle in a superconductor. And band structure theory can be applied to all these cases irrespectively. So let us look at the first simplest case, which is the case of a single orbital band structure. So if you think about a material, materials are made of atoms, of course, and atoms have different types of local orbitals. So you can have s electrons, like in hydrogen, you can have p electrons, like in carbon, you can have d electrons, f electrons, and so forth. So for a generic complex material, usually the orbitals that matter are a combination of these spd electrons. For the sake of simplicity, we are going to first focus on a case where only one orbital matters, and without caring too much about which orbital is the one that matters. And what we are going to take is that we have one relevant orbital in each atom, and that the orbitals are orthogonalized, meaning that even though we have, let's say, atoms at a certain distance and the orbitals have some finite overlap, we just make a linear combination of those orbitals so that we can find a local basis that where the overlap between different orbitals is essentially zero. This is just an assumption that can be performed systematically using something called linearization that we will discuss during the contact session. So the idea is that we take this orthogonal basis, and in this orthogonal basis, we will write our Hamiltonian. And even before writing the Hamiltonian, we know we can already make a guess about how the eigenstates of the Hamiltonian are going to be, irrespective of what its exact form. If we have a system that has some symmetry, as we discussed in the previous lecture, we can show that the eigenstates of the Hamiltonian are the same as the eigenstates of the symmetry operator. And in particular, when we apply the symmetry operation, we pick a phase every time that the symmetry operation is applied. This phenomenology implies that the eigenstates of the Hamiltonian can be written as a complex phase e to the n phi times the creation operator, where n runs over the indexes of all your sites. And now you can make this exercise first for a finite system that has, for example, 7 sites, for a finite system that has 11 sites, and then for a system that has an infinite number of sites. And what we would get is that in the case where this system has an infinite number of sites, we essentially sum over all the possible phases. And to study solids, we will work in the limit in which we have an infinite number of sites. Okay, very good. So now let's say stop for a minute and think about what is the actual meaning of this phase that we get when we apply the translational symmetry operator. We usually think in terms of a discrete basis in real space, but we could try to make a step back and go to the Schrödinger equation and ask ourselves how the translation operator is written in terms of operators that we find in the Schrödinger equation, in particular, the momentum operator. So minus I, the derivative with respect to x. If you try to write what is the value of the wave function at x plus a as a function of the value of the wave function at the point x, what you can actually show is that that value can be written in terms of a Taylor expansion. So you can make a Taylor expansion, including first derivative, second derivative, third derivative, and so forth. And in that way, you can relate the value of the wave function in x plus a as a function of the wave function in point x. Now, if you ask yourself, well, what would happen if this term that I have in the exponential that comes from the Taylor expansion is treated as a number instead of an actual operator? And that would be the case, for example, in case you assume that the value that you get in this prefactor is just an eigenvalue of the translational symmetry operator. Then what you can identify is that the phase that is picked by the translational symmetry operator is essentially some sort of quasi-momenta times the lattice constant, times how much you actually shifted your system in real space. And this is the reason why we call the symmetry eigenvalue phi as the quasi-momentum, because it's essentially related to the actual momentum that we had originally in the Schrödinger equation. So from now on, let us refer to this symmetry eigenvalue just a quasi-momentum. And of course, we will know that this quasi-momentum goes between, let's say, minus pi and pi. Okay, great. So let us now look at the one-dimensional type bonding model. And we can now write the model explicitly. So we have a one-dimensional system that is composed of an infinite number of sites, and the Hamiltonian of the system is essentially C dagger n Cn plus 1, where we essentially have hoppings between nearest neighbors. This system has translational symmetry, and therefore the eigenstates of the Hamiltonian can be written as e to the I phi n C dagger n. And what we know is that in this diagonal basis, the Hamiltonian is going to be diagonal, because of course this is the basis where both the translational symmetry operator and the Hamiltonian is diagonal. So the way we can compute this is actually relatively simple. So we can take our eigenstates expressed in terms of the original C dagger operators, and we can invert very easily this relation. So this is effectively just a inverse Fourier transform. So if C dagger is related by e to the phi n C dagger, then C dagger has the opposite relation, just because the inverse Fourier transform is the inverse operator to the Fourier transform. We plug those creation and annihilation operators written in terms of the eigenstates into the Hamiltonian. When we plug them into the Hamiltonian, we realize that we essentially have a product of phases, and that product of phases gives rise to a delta function that picks the e to the I phi phase once and the e to the minus I phi phase once. when you consider those two terms, you will essentially get 2 times the cosine of phi, written in the diagonal basis, where each phi is independent from each other. So in practice, what we get is that when we make this replacement of the original creation and annihilation operators in terms of the eigenstates, we get that our Hamiltonian is diagonal, written now in terms of psi dagger and psi, and the prefactor that we have is our eigenstate, that it's 2 times the cosine of phi. And you can very easily plot this relationship and you get essentially the dispersion of a one-dimensional tie-bonding model. Now, in this dispersion, there are several very interesting things that we can notice. So first of all, at the top of the band, the curvature is different than at the bottom of the band. So if you look at the bottom of the band, you can sort of realize that there's some approximate parabolic dispersion. But at the top of the band, there's a parabolic dispersion that goes in the other way around. What this actually means is that the effective mass at the top of the band is opposite than the effective mass at the bottom of the band. So at the bottom of the band, we are going to have effectively electrons, quasi-particles with positive mass. At the top of the band, we are going to have what we usually call holes, so quasi-particles with negative mass. This is something that is going to be much more clear when we define the effective mass. And then you see that at zero, it seems as if the energy versus momentum relation is linear instead of the typical quadratic dispersion relation. This is also something very important that we will see again later on. Okay, so maybe I can now ask you a very short question to think on your side. So let's imagine that we have our one-dimensional tie-bonding model, but now instead of having just first neighbor hopping, so coupling between site number I and site number I plus 1, we also have a finite second neighbor hopping. So coupling that it's eta, and this coupling eta couples site I with site I plus 2. So now my question is, well, what would be the dispersion relation of this model? And the way one can simply compute this is by using exactly the same trick as we did before. This Hamiltonian has exactly the same symmetry as our original Hamiltonian, which is translational symmetry. So we know that the eigenstates are going to be exactly the same. Even though the Hamiltonian is different, the eigenstates are the same. And so we can do the very same trick as before, and by doing it, we will see the dispersion relation. You can do it on a paper, and after doing it, you will see that the correct option is option number A. So we essentially have 2 times the cosine of phi plus 2 times eta cosine of 2 phi. Okay, very good. So now let us move to multi-orbital band structures. These are, let's say, more complicated cases, but they are also much more interesting cases. So if you think about the models that we need to consider in order to study topological insulators, including quantum spin Hall insulators, Chern insulators, topological metals, and even Dirac materials, then we need to rely on multi-orbital band structures. Okay, so now we are going to first focus on the one-dimensional case. So what we are going to assume is that we have a system that can be built by replicating some fundamental unit. And that fundamental unit is essentially this black square that has orbitals 1, 2, and 3. So what we are going to do is the number 1, 2, and 3 is going to be an index of our creation operator. It's going to be the index alpha, and then this building block is going to be replicated in real space several times. So, and the index of this replication is going to be another subindex n, which labels the index of the unit cell. And so if we start thinking about what is the most generic Hamiltonian that we can write for such system, that it's bilinear in fermionic operators, then you can very easily come up with this model. So you essentially have hoppings between orbitals in the same unit cell. Those hoppings are the T alpha beta. These are what we will call intracell hoppings. And then we can have hoppings between sites in different unit cells. So in unit cell number 1 and unit cell number 2. Those hoppings are what we call the intercell hoppings gamma alpha beta. In this Hamiltonian, we write them just between one unit cell and the next unit cell. But in general, you could have couplings to not only the next unit cell, but next to next, next to next to next, and so forth. The tricks are always the same, but let us, for simplicity, focus on this case with only first nearest cell coupling. So the trick to diagonalize the Hamiltonian is actually very similar to the one that we used for the single orbital model. Now, what we have to think is that instead of having just simply a symmetry that consists on taking site number n and transforming it in site n plus 1, we can have a much more generic symmetry. We can have a symmetry that not only transforms site number n to n plus 1, but that also makes some unitary rotation in the orbitals that we have in the unit cell. So in general, when we apply the symmetry operator to our eigenstates, what may happen is that we know not only transform C dagger n alpha to C dagger n plus 1 alpha, but that we also make a rotation in this orbital subindex within the unit cell. So since now we have this degree of freedom, since now we can have these more generic wave functions, what we know is that the eigenstates are going to be some arbitrary rotation inside the orbitals in each unit cell times a phase, which is the formula that you see on the left. Now, if we make the right choice for this unitary transformation, we know that the Hamiltonian can be written in a diagonal form. So the question now is, what is the unitary transformation that we must make in order to for the Hamiltonian to be completely diagonal, both in the symmetry eigenvalue phi, but also in the orbital eigenvalue alpha? And the answer to this question is that we simply need to make the unit transformation that diagonalizes this Hamiltonian h of phi, t mu nu plus gamma mu nu e to the I phi plus the Hermitian conjugate. And the way to reach this conclusion simply comes from just plugging in the definitions of phi that we have in this slide onto the Hamiltonian and enforcing the resulting Hamiltonian to be diagonal. Then that will quickly show you that the unitary transformation that we need is the transformation that diagonalizes that matrix H of phi. Okay, good. So now we know how to go from a real space basis of a Hamiltonian with several orbitals per unit cell to the diagonal basis, to the basis where the Hamiltonian is completely diagonal. So now a question for you is, what would be the dispersion relation? What would be the relation between the eigenstate and the symmetry eigenvalue phi for this Hamiltonian? So this Hamiltonian where we have two orbitals per unit cell, orbital number A and orbital number B. And then we have strong coupling within the unit cell, and then a weak coupling between this unit cell and the next one. And the coupling is eta. So there are two options. Option number A is the plus minus the absolute values that you see, and option number B is 2 cosine of phi, 2 eta cosine of phi. Please write down this on a paper, and after writing down the matrix that appears in the previous slide, you will very quickly realize that the correct option is option number A. And this just comes from the fact of just writing the effective 2x2 matrix that has to be diagonalized. And you see that in this 2x2 matrix, the terms in the Hamiltonian enter in the off-diagonal. So you have a 1 for the coupling within the same unit cell, and then for the coupling to the next unit cell, you have eta e to the minus I phi in the top right, and eta e to the I phi in the bottom left. And of course, the eigenvalues of this Hamiltonian are just plus minus the absolute value. This is a Hamiltonian that it's going to appear again when we look at topological matter. But from now, at this stage, let us just remember that we can compute eigenvalues for multi-orbital Hamiltonians just following this strategy. See how many orbitals you have in a unit cell. This determines the size of the matrix that you have to write down. And then in this matrix, you include the hoppings within the unit cell as the numbers that you read from the Hamiltonian, and the hoppings to the next unit cell as the right elements in the matrix, but now with a phase, because that is the phase that comes from the symmetry eigenvalue. And this is a procedure that you can apply systematically, and it comes from using the very same mathematical trick that we used before. Okay, very good. So now let us look at higher dimensional bond structures. And these are maybe the most interesting cases from the electronic structure point of view, because we can have, let's say, much more rich phenomena arising. And first, as a reminder, let me tell you again how we can deal with infinite two-dimensional or even three-dimensional or four-dimensional systems with an infinite number of sides. When you have a two-dimensional system, for example, that has periodicity, now you have two different operators that commute with the Hamiltonian. There's the operator Tx that essentially moves our system one side to the right, and we have the operator Ty that moves our Hamiltonian one side up. And these two operators are independent. They commute between each other, and they also commute with the Hamiltonian. So now your eigenstates can be simultaneously eigenstates of Tx, they can be eigenstates of Ty, and they can be eigenstates of the Hamiltonian. So we are going to work on the basis where Tx is diagonal and Ty is diagonal and the Hamiltonian is diagonal. So in this way, you can essentially label your states according to the phase that they pick when you apply Tx, the phase that they pick when you apply Ty, and of course, the energy that you get when you apply the Hamiltonian. And in particular, this labeling of the states essentially tells you that there's going to be a mapping between the phases phi x and phi 1, phi y to the energy. These phases live in this square space that goes from 0 to 2 pi for phi x, 0 to 2 pi for phi y, and this is what we call the reciprocal space. And in particular, this is what we call the first Brillouin zone. You can relate these phases actually to a physically meaningful observable, which is, again, the wave vector. And the way to relate it to the wave vector is by using, again, the argument of how this phase is related with the original momentum in your Hamiltonian in this Schrodinger equation. And in practice, what you can see is that the phase phi x is effectively some effective quasi-momentum times the first lattice vector, and the phase phi y is some effective quasi-momentum times the second lattice vector. And this is essentially the way we can label all our eigenstates in 2 dimensions, and we can, of course, extend this very easily to 3 dimensions and even higher. So from now on, let us focus on what is the mapping between phi x and phi y to the energy. One more thing that it's important to keep in mind is that, of course, this square space is not an open space, but it's actually a periodic space, meaning that phi x equal to 0 is the same as phi x equal to 2 pi, and the same for phi y. So if you identify the left and right sides and the bottom and top right sides, what you can actually see is that the 2-dimensional Brillouin zone is effectively a torus. So it is essentially a closed surface due to the periodic boundary conditions. And this is going to be important when we study topology, in particular when we learn how we can map the two-dimensional space to a topological invariant. Okay, so now let us do a very simple exercise. So let's imagine that we have a very simple tie-binding model. This is a single orbital model in a square lattice. So we have one orbital per unit cell. We have hopping to the unit cell that we have on the right. We have hopping to the unit cell that we have on top. And this is usually what we represent as sum over first nearest neighbor. So say that we have on the left, on the right, on the bottom, on the top. And my question for you is, what is the dispersion relation of this? The way this can be computed is just using the very same trick that we use for the one-dimensional system, but just twice, once for the x direction, once for the y direction. And if you do that, you will see that you are going to pick just two faces. You will pick the face in the x direction once, and this will give rise to 2 times cosine of kx or phi x. And then if you do the same procedure, if you follow the same procedure for the y direction, you will pick the face in the y direction once again. And this will give rise to an additional 2 times cosine of ky or phi y, depending on how you write it. This is the dispersion relation of the two-dimensional square lattice. One can use the same trick in 3 dimensions. So now let us imagine that you have the simplest 3-dimensional tie-binding model, one orbital per side on a cubic lattice, and you have hopping to the left, right, bottom, and top, and also on the 3rd dimension. You can use the same trick that we use for the linear chain, not once, nor twice, but 3 times. And if you use that trick 3 times, you will see that you will pick each face for each direction once. So once for the Ka, once for the x direction, once for the y direction, once for the z direction. So that gives rise to this dispersion relation. And you can, let's say, systematically do this for 4 dimensions, 5 dimensions, 6 dimensions, and so forth. The trick is exactly the same. We are all the time exploiting the fact that our eigenstates are simultaneously eigenstates of the Hamiltonian and every single translation operator that we have in our model. Okay, now let us look at some interesting macroscopic properties that we can extract from the electronic structure, in particular that we can extract from the relation between the symmetry eigenvalue and the eigenvalue of the Hamiltonian. So the most important thing to note is that many properties of electronic systems are related to how the quasi-momentum is mapped to the energy. And maybe the simplest property that one can consider is just counting how many energies the system has in a certain energy interval. And a systematic way of writing this down is just by writing the delta function of the frequency minus the energy as a function of the momentum integrated in the whole momentum space. This is what it's called the density of states. And it essentially tells you what is the density of states at a certain frequency. So how many states do you have at a specific energy? This is going to be extremely important when we deal with interaction. When we look at systems that have either repulsive interactions, such as systems that develop magnetic order or charge density wave order, and systems that develop superconductivity. The density of states essentially determines how easily a system is affected by interactions. If your density of states is very large, and in particular if it is infinite, then interactions very quickly impact your system. If your density of states is not infinite but finite, then you may need some finite interaction strengths to get something new in your system. And if the density of states is 0, then electronic interactions have a hard time making any effect in your system. Okay, great. So now there's another very important object, which is effectively called the group velocity, and it's the derivative of the energy with respect to the quasi-momentum. So you can think about this as the slope of your dispersion relation. This is called group velocity because if you think that your energy versus momentum is k squared, this essentially gives rise to the conventional velocity. And the deal is that for electronic structures, we can define this generalized group velocity that can take different values in different points in the Brillouin zone. And this effectively tells us how easily electrons move in a material. If our group velocity is 0, meaning that the eigenvalues do not depend on the momenta, then electrons are sort of localized. They are not moving in space. If this group velocity is very high, electrons are not strongly affected by scattering, for example, and so forth. Then there's another very important object, which is called the effective mass. And in practice, it is just the curvature of the electronic dispersion. So you can compute it systematically by computing the second derivative of the energy with respect to the momenta. And this essentially allows you to see what is the mass that electrons are feeling when they are in that electronic structure. This is in practice, the mass that you will measure when doing any experiment in a material. You will not measure the original mass of the electron. What you are actually going to measure is this derivative. And in this way, you can have materials where the effective mass of the electron that you measure is very high, even infinite. And you can have materials where the mass of the electron that you measure is almost non-existent, even is 0. And this all comes from the different dispersion relations that you can have in different electronic structures, depending on the hopping, depending on the geometry, depending on any fine-tuning that you make to the tie bonding model. And then the last important term, or the last important observable to consider, is what it's called the Fermi surface. This is essentially the collection of points in reciprocal space that have a very specific energy, and that in particular that have the energy of your highest occupied electronic state. Fermi surface is an extremely important object also when looking at electronic interactions. So shapes of Fermi surfaces actually will tell you which electronic interactions and which instabilities are more likely to occur in a material. It also tells you about how the material behaves in a magnetic field, and it's one of the observables that you can see with ARPES. Okay, so let us look now at 3 very specific cases of electronic dispersions. And these are, let's say, very simplified limiting cases. And of course, real materials have a mixture of the 3 many cases, but this is essentially 3 specific scenarios that are very useful to consider. So the first one is just having parabolic bands, meaning that your energy versus momentum relation is quadratic. This would be the case of free electrons, for example, and it's the case that happens in most of semiconductors and metals. So in these cases, most of the observables and phenomenologies that you see are what you would expect from a p²/2m dispersion relation. This is, of course, extremely important from a technological point of view. So most of our electronics are based on these parabolic bands, in particular in semiconductors. There are, nevertheless, more interesting cases. And one of the interesting cases is the case where the energy versus momentum relation is linear. So instead of having E proportional to p², we have E proportional to p, proportional to the momentum. And this is what happens in graphene. And it's what happens in different types of topological matter, including quantum spin Hall insulators, Chern insulators, symmetry-protected topological phases, and so forth. And some of the very interesting phenomena that happen here is that this linear relation gives rise to a Hamiltonian that actually has topological properties, that has finite invariance, such as very phase, and that has very specific transport properties that we will discuss in the topology lecture. And of course, something very interesting is that this linear relation is very similar to what we expect in, let's say, relativistic physics. So much of the phenomena that one can expect at relativistic energies actually happen in these materials that have linear relation. From the mathematical point of view, they are effectively the same. And then we have a third case, which is the case of flat bands, which is, one could think, maybe the most boring case for an electronic dispersion. So you have an energy that does not depend on the momentum at all. It is completely flat. Even though this seems relatively trivial, flat bands are extremely interesting. And the reason why they are interesting is because the flatness of the band actually gives rise to a divergence in the density of states. So you have an infinite number of states at very specific energies, which in turn leads to very strong effects when you include electronic interactions. Furthermore, if these flat bands arise due to a non-trivial reason, such as a magnetic field or some modulation in real space, then flat bands may have topological properties. They may have finite Chern numbers. And this is of great importance, of course, in the quantum Hall effect. And it is of great importance also in moire materials. Of course, you can also have flat bands if the hopping between your orbitals is zero, but those flat bands are, let's say, relatively trivial, and they are effectively like isolated orbitals. Okay, so now let us look at how these different dispersions can arise. So first, let us look at the parabolic dispersion, and this is something that we briefly mentioned before. If you look at the one-dimensional tie-bonding chain, then we had this dispersion that was 2t cosine of k. You can systematically do a Taylor expansion around the minimum or maximum. And when you do the Taylor expansion, you see that you have an energy versus momentum dependence that is effectively k-squared. So parabolic electrons can very easily appear in generic band structures, in particular when you are at the very top of the band or at the very bottom of the band. So that is the reason why semiconductors usually have parabolic dispersion relations, because in a semiconductor, you effectively have, let's say, a gap, and then just a few electrons in your band or a few holes in your band, so you are always at the top or at the bottom. And in the one-dimensional chain, this is something that happens, let's say, in both two places. So you have parabolic dispersion at -2, you have parabolic dispersion at +2. The interesting point is that they have opposite effective masses because they show opposite curvatures of the bands. Tie-bonding models can be systematically solved using computational methods. They are, of course, can be done also using analytical methods. But if you have a multi-orbital model, it is often very hard to actually solve them analytically. And there are, of course, many tools to solve tie-bonding models. In this course, we are going to use one main tool that it's called Pycula, that it's a Python package that allows you to set up different tie-bonding models, compute band structures, density of states, include interactions, compute Fermi surfaces, topological invariants, and so forth. There's also a user interface that we will use at some points to very quickly see how electronic dispersions change. And these are essentially the computational methodologies that one will use during this course for understanding electronic structures. Okay, now let us move on to a more interesting tie-bonding model, a more interesting dispersion, which is the case of a honeycomb lattice. A honeycomb lattice is just a lattice that has two orbitals per site, and the lattice in real space is effectively triangular. So you have a two-orbital basis. Your Hamiltonian has two orbitals per unit cell, and then you replicate it following a triangular lattice. If you now write down what are the different intra-cell hoppings and inter-cell hoppings and solve the Hamiltonian, what you will see is that the dispersion that you get is the plot that you observe on the right. You can do that analytically. You can also do that with the computational package that we will use. And when you do this, you easily realize that there are two very special points in reciprocal space that here we call K and K prime, where we have something like a cone. We have a linear dispersion relation at low energies, and these are effectively the points that are important for the physics of graphene, for the physics of a honeycomb lattice made of carbon atoms. There's lots of very interesting physics happening at these energies, and this is something that we are going to look in detail in the topology lecture. A way of understanding this from an analytical point of view is just by doing a low energy expansion to your block Hamiltonian. So if you take the honeycomb lattice and you try to write down the block Hamiltonian, you will see that you only have off-diagonal elements in your Hamiltonian, because effectively you only have couplings between opposite sublattices. So there's hopping from A to B, from B to A, but not from A to A and not from B to B. These off-diagonal elements become zero at some points in momentum space, and at those points in momentum space, you can expand them using a Taylor expansion. And in particular, in your Taylor expansion, you're going to have two linear terms, one term for the real part and one term for the imaginary part. And that is what we call Kx and Ky. If you only retain the linear terms, what you actually see is that the effective Hamiltonian that you obtain is just the Dirac Hamiltonian, where you have Kx sigma x, Ky sigma y. And of course, the eigenvalues of this Hamiltonian are essentially the square root of Kx squared plus Ky squared, which in practice means that your dispersion relation is linear with the momentum. And then one can also come up with a very simple model that features flat bands. So this model is very similar to a square lattice, and it can be built from a square lattice, but the idea is that you essentially remove one side every 4 from the square lattice, and this is what it's called the Lieb lattice. This is a lattice that has a dispersion relation that in a way is similar to the square lattice. So you have, let's say, a parabolic band on the top, parabolic band on the bottom, but apart from that, you have a flat band at 0 energy. You have a band where the energy does not change with the momentum. And this has been a very interesting model to study the effect of interactions in solid state systems. And we can actually have many different systems that have flat bands due to some very special geometry that translates onto an interference in real space that localizes the electrons. And in particular, some of these models that can show flat bands and that are not the Lieb lattice are, for example, this Kagome lattice, which in practice is as if you take a triangular lattice and you remove one side every 4. In this model, you get a dispersion relation that it is actually similar to the honeycomb lattice. So you actually have Dirac cones at some energies, but something that is more special is that you actually have also a flat band at the bottom of the band. So you have, again, a band where the energy does not depend on the momentum at all. And of course, this flat band also appears because of interference in real space. Okay, so now let us move on to the last part of the lecture today, which is how we can measure band structures. Of course, the eigenvalue of the symmetry operator seems just like a mathematical trick. The eigenvalue of the Hamiltonian may be more physically meaningful, but at least the eigenvalue of the symmetry operator may be like a physical, like a mathematical trick. So one very important question is whether if this symmetry eigenvalue, which we called the momenta, is something that we can observe in reality or not, and maybe even phrased in a more ambitious way, can we observe the relation between the quasi-momenta and the energy in a real material with some measurement? The answer is yes. And this can be done using angle-resolved photoemission spectroscopy. The basic idea of this measurement is that you effectively shoot photons to your material. These photons interact with the electrons, and there's a transfer of both momenta and energy. And since momenta and energy have to be conserved between the incoming and outgoing photon, then you can somehow map the momenta to the energy of your electrons. And using this trick, you can effectively measure band structures using ARPES. And in particular, here on the left, you see the band structure of graphene, where you see that the dispersion relation is very similar to what we saw before in the tie-banding model. And you can also look at the Fermi surface, at the collection of points in reciprocal space that have the same energy corresponding to the highest occupied orbital. So ARPES is a extremely useful tool to see if models that we have for materials correspond to the reality. And one can very often make systematic comparisons between electronic structures and ARPES measurements. So this is everything that I wanted to tell you today. So if I could ask you to remember something, please remember that in periodic systems, we can compute the eigenvalues of an infinite dimensional problem using band structure theory, which in practice means using this trick of choosing the same eigenbasis for the symmetry and for the Hamiltonian, and that we can actually learn a lot about the properties of a material just by looking at the dispersion relation, at the relation between the eigenvalue and the quasi-momenta. Thank you so much for attention, and see you in the next recording.